Logarithmic functions. Logarithms are an operation used to solve equations that are in the form y equals b to the power of x, exponential equations. So if you have a variable exponent, you need logarithms to solve that. Logarithms can also be found in formulas for the Richter scale that determines the intensity of earthquakes, sound intensity, light density, things like that. In this section, we're just going to learn our formulas and how to work with logarithms. So first, we need to be able to transfer back and forth between logarithmic form and exponential form. So both forms have the same letters in the formulas, they're just rearranged. The b stands for base in both the logarithm and the exponential function, b for base. And then notice the x and the y swap sides when you do rearranging. So you're going to be asked to go back and forth between log form and exponential form. Our first example says to write it in exponential form, 4 equals log base 3 of 81. I like it flipped around the other way to get started. It fits our formulas a little bit better, so I'm going to flip it around and write log base 3 of 81 equals 4. Then I always think about the little base growing up and becoming a big base, and then the 4 and the 81 will switch sides, so it will be 3 to the 4th power equals 81. Now when you're writing things in exponential form, you can always check them. It should be true. 3 to the 4th power does equal 81. Let's try another one. Negative 2 equals log base 6 of 1 over 36. Flip that around. Log base 6 of 1 over 36 equals negative 2. Now our little base, the 6, grows up and becomes a big base. The negative 2 and the fraction flip sides. And the reason why this is true, and we're going to review this a little bit later, is that a negative exponent causes numbers to flip over. So 6 to the negative 2 is 1 over 6 squared, which is how we end up with 1 over 36. So that's going from log form to exponential form. It's in exponential form. Now we want to write it in log form. Now my base is the 4. So my big base shrinks back down, becomes a little base again. And the 8 and the 3/2 change sides. Let's try the next one. 2/3 cubed equals 8 over 27. 2/3 is the base. So my big base shrinks back down, becomes a little base again. And the 8 over 27 and the 3 change sides. Logarithms. We never leave values in radical form. Rather, we convert them to values with fractional exponents. And here is the formula to convert back and forth between radical form and exponent form. The little number on the outside of the radical goes on the bottom of the fraction, and the exponent on the inside goes on the top of the fraction. So here's some examples of how that works. The 4th root of x cubed. So if I want to write that with a fractional exponent, the 4 goes on the bottom of the fraction, the 3 on the top, and you have x to the power of 3/4. The next one, the 5th root of x. Keep in mind that x without any exponent has an understood 1. So that's how we get x to the 1/5. The one that you'll come across the most is square root. With square root, you need to understand that there's an understood 2 on the outside with our understood 1 on the inside. So square root converts to a fraction of 1/2. Now, with all that in mind, let's go back to writing in log form. And if you come across one like this that is the 5th root of 32, before you can start, you need to convert that to fractional exponents. So 32 has an invisible 1 exponent. It will be 32 to the power of 1/5. So we always do that in problems when we're dealing with logarithms. Now 32 is the base. My big base shrinks down, becomes a little base again. And the 2 and the 1/5 switch sides. The next examples ask us to evaluate without a calculator. So it's easiest if you'll make this into an equation, log base 7 of 49, by writing equals x. And then we can rearrange into exponential form. 7 is the base, so my little base grows up, becomes a big base. 7 to the power of x equals 49. And then you just have to think, you can use your calculator or just hopefully think inside your head, 7 to what power is 49? 7 squared. So x would have to be 2. The next one is similar. To get it going, we want to write equals x, make it an equation, then rearrange. Little 3 grows up, becomes a big 3. The x and the 27 change sides. So you think, what 3 to what power is 27? It's 3 to the third, so x is 3. Now, of course, these can be much more complicated. What if it was 3 to the power of x equals 20? And there's not a whole number answer for that, but we'll get to that in another section. To do the next example, we need to have a little bit of a review about negative exponents, like we saw in a previous example. Remember, negative exponents cause the base number to flip over, and then the exponent becomes positive. So if we're looking at 3 to the power of negative 2, the negative 2 makes our 3 flip, and it's 1 over 3 squared, which becomes 1/9. Or if the negative exponent is in the bottom of the fraction, like 1 over 4 to the negative 3, the 4 flips back up to the top, exponent becomes positive, and you have 4 cubed, which is 64. So we need to keep that in mind as we do these next problems. We're still doing evaluate without a calculator. We still want to write equals x, and we still want to rearrange. 3 to the power of x equals 1 over 9. Well, we know that 3 squared is 9, but what would make it flip over and become 1 over 9? Well, an exponent of negative 2 would do that. If it was 3 to the negative 2, then that would be 1 over 3 squared, which is the 1/9. So x has to be negative 2. For the next one, we have a radical. Don't ever leave it a radical. Always change it to a fractional exponent. So it equals x. And rearranging, we have 5 to the power of x equals, and then a square root is the exponent of 1/2. Now, if these two sides are equal, and the bases are the same, for the two sides to be equal, that must mean the exponents are also the same. So x is 1/2. Take a look at some properties of logarithms. Here are several properties. I'll give you the property and then an example. Number 1, log base b of 1 equals 0. That means the log of any base of 1 always comes out to be 0. So for the example, log base 16 of 1 has to equal 0. Property number 2, log base b of b equals 1. If the little base and the number beside it are the same number, then the result is just 1. So for our example, log base 0.5 of 0.5, the little base and the number are the same, so it equals 1. Property number 3 is similar. Log base b of b to the x equals x. So this time our little base and our regular number are the same, but we're going to have an exponent now, so the answer is just the exponent. So our example, log base 4 of 4 cubed, since the 4's are the same, the answer is just the exponent, which is 3. Now, you'll come across problems that are tricky. It doesn't look like it fits that property, but if you do a little readjusting, it will. Log base 3 of 81. Well, 3 and 81 are not the same number, but 81 is 3 to the 4th. So if you can make the big number have a base the same as the log's base, then you can fix it so that the answer is just the exponent. And in this section in your homework, it will always work out that way. that the number that they give you, like this 81, can be rewritten with a base the same as the little base. And then finally, property number 4, b to the power of log base b of x, the b and the log b just sort of cancel each other out if the bases are the same, and you get x. So an example would be 5 to the power of log base 5 of 7. Since they both have 5s, they're going to cancel, and you're just left with the 7. And then another little thing to know about, if you have a logarithm that doesn't have any base at all, it's an understood 10. So if it just says log x, it's understood that the base is 10. All right, so using these properties, we want to try and evaluate, and it says evaluate without a calculator. So let's put in our secret base 10 here and see if we can use property number 3. I can rewrite this as log base 10 of 10 to the 3rd power, because 10 cubed is 1,000. And now that the 10s are the same, this all just kind of goes away, and the answer is the exponent of 3. Log of 10 to the 8th power. Again, invisible base 10. So then the 10s are just going to cancel, the log 10 with the big 10, and it's just the exponent, which is 8. 10 to the power of log 9. So if I fill in my invisible 10 base, then I have property number 4. Since the 10s are the same, the answer is just the 9. If a logarithm has a base of the number e, it's called a natural logarithm. So log base e of x is the same thing as ln of x. ln is for natural logarithm. The natural logarithm has properties similar to what we call the common logarithm, which is just the log log. Property number 1, the natural log of 1 is 0. Property number 2, the natural log of e is 1. Natural log and e are inverses of each other, so they cancel each other out. Property number 3, natural log of e to the x is x. So in the example, we have natural log of e squared. The natural log and the e cancel each other out, and you're just left with the squared, with the 2. Number 4, e to the power of natural log of x equals x. So in the example, e to the power of natural log of 8, the e and natural log cancel, and you're just left with 8. And then one last little thing. If you are trying to take the log or the natural log of any negative number or of 0, so if it's less than or equal to 0, then it is undefined. You can't take the log or natural log of a negative number or of 0. It cannot be calculated.